Hello guys, welcome to this lesson titled The Number System. My name is Akosmaila and I'm going to do the presentation for this lesson. What is the essence of this topic titled The Number System? This lesson has been prepared thoroughly to help you understand and be able to categorize the various types of numbers that you will come across in your mathematics journey. So guys, enjoy the ride. So the number system. There are a lot of categorizations or categories of numbers in this world. The biggest of this category is what we call the complex number system. All numbers in the world are represented by C, and C means complex numbers. These numbers consist of real numbers and imaginary numbers. So diagrammatically, we have every complex number system. In every complex number system, we can decompose the numbers or the entries over there into two parts. We will have a real number parts and we have imaginary number parts. General forms of complex numbers. How do we actually represent complex numbers, or how do we actually form complex numbers? Every complex number A is represented as A plus BI. So we have A equals A plus BI. And actually, any number at all in this world can be decomposed into this form, where small a is a real number part and BI is called the imaginary parts. Every number falls into this category. Example, 2 can be represented as 2 plus 0i in the complex number system. 5 can also be represented as 5 plus 0i in the complex number system. So meaning all the numbers that we come across in mathematics falls into this category. Just that in disguise, the 0i is represented in disguise. Why is it so? So you get to understand why the 0i attached to all these numbers have been erased, or we no longer see them in our level of mathematics. The complex number system, to be frank, it is not in our syllabus. So that is why in our syllabus, all the numbers that we come across in books don't have the 0i attached to it. It only has the real, or they only possess the real parts. Let's learn this basics about imaginary numbers. I is the square root of -1, which is an imaginary number. So we say I equals root of -1. If you have the square root of any negative number, there is no real solution. This implies that the square root of any negative number does not have, or that doesn't have, a real number solution. So when you come across a problem like this in your level of mathematics, your teachers will tell you that the solution doesn't exist. They are right. The solutions doesn't exist in the type of numbers that the syllabus prescribe, which is the real numbers. However, there is an imaginary solution. So it is not that it is impossible. There's a solution, but the solution is not a real number. It is an imaginary number. You can factor out the negative and represent that as I. Then square root the positive version as normal. So meaning that whenever you have a square root of any number, you can factor the roots of -1 out of that particular number and just take the roots of the perfect number, and with that we all know how to do it. Example, you can use the number I to rewrite root of -25. You have to factor out -1, so you are going to get roots of -25 will be equal to the square root of -1 times negative times 25. And you can also separate them as root of -1 times root of 25. And we actually know the root of 25, which is 5, and we know the root of -1, that is at the top over there, is said to be I. So which means that the root of, or square root of -25 is, or the answer is 5i. So when you take the square root of -16, you are going to get 4i. So now we come to real numbers. So as we move along, the imaginary numbers have been discarded, and now we are dealing with only the real number part of complex numbers. So what are real numbers? Real numbers consist of all numbers that can be represented on a number line. and they are represented by R. So in books, wherever you see this symbol R, it denotes the complex number sets. The real numbers include natural numbers, whole numbers, integers, rational numbers, irrational numbers. So we have a diagrammatic representation of the categories of numbers. So at the top there we have the complex number system. Then at the bottom of it, it has also got two branches, which is the real numbers part and the imaginary numbers part. And you can see that imaginary numbers has now been discarded along the line, and we are dealing with only real numbers. And the real numbers also have rational numbers and irrational numbers. And irrational has also been discarded. So we are now dealing with integers, whole numbers, natural numbers. So in subsequent slides, we'll be talking about each of these categorization. Categories of numbers in the real number system. So these are the composition of the real number system. Natural numbers, whole numbers, integers, rational numbers, irrational numbers. So what are the natural numbers? Natural numbers are the set of counting numbers. And this set is or comprises 1, 2, 3, 4, 5. And the subsequent successors also obtained when you add 1 to the previous number. And this list continues forever. So it is only positive numbers that are over here, no fractions, no decimals, unless it will simplify to a whole number, such as 6 over 2 will give us 3, 4 over 2 will also give us 2, 10 over 5 will also give us 2, or you can have 16 over 4, which will give us 4. We don't actually have 5, something like 5 over 2 is not a natural number. The set of natural numbers strictly contains only these positive numbers. 0 is not included because we don't count 0. So 0 is not a natural number. What are whole numbers? All of the counting numbers and 0. So which means the whole numbers simply comprises all the natural numbers with 0 added. So this list is 0 plus the natural numbers, then 0 and positives, no fractions, no decimals, unless it simplifies to a whole number. Now we come to the set of integers. The integers are all of the natural numbers, their opposites, and 0. So which means that the set of integers contains both natural numbers and their negatives, whole numbers and their negatives. Think of numbers on a number line. Positive or negative whole numbers and 0. No fractions, no decimals, unless it simplifies to an integer or a whole number. So which means that the set of integers has nothing like a fraction inside. 1 over 2 is not an integer. 3 over 6 is not an integer. But when you have 6 over 3, it will simplify to 2. So that one becomes an integer. You have to take note of that. Let's look at the properties of the integers. So every integer assumes or possesses this property. Or these properties also exist in the set of integers. Property number 1, closure. When you add any two integers and the result also gives you an integer, then we say that or we term that property as closure. So we say the set of integers is our addition is closed in the integers. Meaning that when a plus b gives us an integer value where a and b are any integers. So when you add any two integers and you get an integer back, we say that the property is closed, that property is termed closure. At the same time, if you also multiply two integers and the result becomes an integer, then we also say that, we also term the property, we also term it as being closed. So it all falls under the closure property. Second, additive identity. When you take any integer, there is a unique element e, such that when you add that e to a, you come and get a back, where a denotes any integer. And you can think of this particular e, the identity element, as being equal to 0. So which means that 0 is the additive identity in the set of integers, because when you add 0 to any other integer, you get the same integer back. 3. Multiplicative identity. So multiplicative identity means that there exists a unique element e in the set of integers, such that anytime you multiply this e by any other integer, the result becomes the integer again. So we have a times e equals a, and this e, the multiplicative identity in the set of integers here, is equal to 1. So basically 1 times any other integer will give you the integer back. Multiplicative inverse. A times y equals 1 for some integer a. The only two positive integer a here are 1 and negative 1. So if you have an integer and you are able to find another integer which when multiplied by the first integer gives you 1, then we say that the second integer is the multiplicative inverse of the first one. So over here we have an integer a, and we have been able to find another integer y, and both of them multiply gives us what? 1. It means that y is the multiplicative inverse of the number a here. So actually, it means that when you find the multiplicative inverse of a number and you multiply it by that number, the result becomes the multiplicative identity. And the only two integers that possess or that have multiplicative inverses are 1 and negative 1. No other integer again. Then we have the associativity property, which is common to all of us. A plus B plus C at the same time being equal to A plus B in bracket plus C. And where A, B, and C are all integers. Then we have the distributive property also here. So in a set of integers, multiplication is distributive over addition. So when you have a multiplying a bracket, you can expand it as ab plus ac. Then we have commutative for both addition and multiplication. A plus b will be equal to b plus a. When you have two integers, no matter the way you position and add them, the result becomes the same, and that property is termed commutativity. When you have two integers, no matter how you position to multiply them, the results become the same, which is termed as commutativity. Additive inverse. The additive inverse of any integer a is that unique integer y, which when added to a gives us 0. For any integer a you pick from this set, there exists another unique integer y, which when added to a gives out additive identity 0 back. Examples. Additive inverse of 2 is negative 2, since 2 plus negative 2 gives us 0. Additive inverse of 10 is negative 10, since 10 plus negative 10 gives us 0. Additive inverse of m is minus m, since m plus minus m equals 0. Rational numbers. These are numbers that can be represented as a fraction a over b, where b is not equal to 0. You can never have a rational number where the denominator is equal to 0. This set includes the integers, fractions, and terminating decimals and repeating decimals. When you have a fraction and its decimals terminates finitely, then we can term it as a rational number. Or if you have a fraction whose decimals recurs, when you have a recurring decimals such as 1 over 3 will give us 0.33333, then we say that that fraction is a rational number. It is not every fraction that is a rational number. Fractions whose decimals doesn't terminate or recurs are said to be irrational. We will deal about it in subsequent slides. So when you have 13 over 4, for instance, is a rational number. Negative 25 over 100, for instance, is equal to negative 0.25. So you can see that with this negative 25 over 100, its decimal point terminates to a finite element, which is 0.25. So those are the only decimal point that you can get for this particular fraction. So hence we say that it is a rational number. Then what are the irrational numbers? Numbers that cannot be expressed as a fraction of integers. In a decimal form, they are the numbers that go on forever without a repeating pattern. Some examples. So when you have an irrational number and you take their decimals, you see that their decimals goes on forever without any definite pattern. And actually, your calculator just tries as much as possible to just cut it short for you. But behind the bar, it goes on forever. So, for example, root 2, which is equal to 1.4142. Pi is an irrational number. 45.9492 is also an irrational number. The easiest way to finding irrational numbers or obtaining irrational numbers, for your information, when you take the square root of any number that is not a perfect square, the resulting decimal will be non-terminating and non-repeating. Therefore, those numbers are always irrational, which means that apart from the perfect squares 4, 16, 36, 25 going, any other number which is not in this category, the square root of that number will result in an irrational number. So we have a Venn diagram that's sought to summarize the whole of this lesson for us. So we have rational numbers here, we have the integers, we have the whole, we have the natural, and we have the irrational numbers falling apart. So which means that when you take a set of rational numbers, in it you will have integers, whole, natural, but irrational numbers do not belong to the rational numbers. So irrational numbers, as you can see, it has been set apart. So the natural numbers, whole, integers falls under, or they are subsets of the rational numbers. So guys, thank you very much for watching this lesson. And also, if you have any other question, you feel free to put it across in the comment box for us. And also, we will try as much as possible to solve questions that have been given to us. Thank you. Enjoy the other lessons. Bye.